Oh, good morning. Good morning.
Hey, how's it going? Sorry, I had some issues logging on using the app. I don't know why.
No, no problem at all.
All
How you
right.
doing this morning?
Good. How are you guys?
Good. Good morning,
Doing
Dr.
well, doing well.
Masters.
So
Okay.
Randy was like one of my mentors when I was in grad school.
Oh, wow.
So
Oh, wow.
I've known her since 2009.
Okay, wow. That's really cool.
Yeah.
Yeah,
Yeah.
Taryn told me that you two knew each other, but I didn't know the exact relationship. So,
Yeah. So she was a few years ahead of me, and she was the first PhD student I worked with when I went to grad school.
oh, cool. Okay.
Yeah.
So we can go ahead and roll right into things if you don't
hmm
mind. I know you're busy, so I want to respect your schedule and stuff. And,
Yeah, no
and
worries.
again, it's supposed to be kind of like a podcast style, so very, very informal.
hmm
If we have to skip some stuff, it's fine. It's not a big deal. So we could always, make cuts or change things as we go along. So,
Sure. Yeah.
but again, really appreciate taking the time.
hmm
All right. All right. So I'm going to kick us off. Good morning. I am Kory, and this is my partner, Parker here. We are both undergrads at MSU Denver, and we're
hmm
currently enrolled in water resources with Dr. Randy Brazeau. Today, we are joined by Dr. Sheldon Masters, an assistant professor at the University of Colorado Boulder. His work centers on how water chemistry influences the release of lead and copper into drinking water systems and how utilities respond to those risks. He earned his PhD in civil and environmental engineering and spent several years working in environmental consulting before entering academia. His recent research has examined corrosion control strategies,
hmm
including the use of orthophosphate and the potential role of higher pH as an alternative approach. In this conversation, we will explore how shifts in treatment strategy may change the way we think about corrosion control and water quality in modern distribution systems. Again, thank you so much, Dr. Sheldon, or Dr. Masters,
Yeah, and you can just
for
call me Sheldon. So that's fine. Yeah,
all right, Sheldon, thank you so much for joining us today. We know you're quite busy, so it means a whole lot to us that you're taking this time to speak with us.
sure.
Rolling right into it, what drew you into civil engineering and specifically into drinking water quality and its distribution systems?
Sure. So I started off having an interest in this because my dad is kind of a civil engineer. So he specializes more on like the land development side of things. So I thought I wanted to work in like land development part of civil engineering. So I got some initial interest in that. And then after a few years, I came across this show on TLC called Extreme Engineering,
Okay,
where
I think I've
they
heard of that.
yeah, where they were talking about like building the world's biggest skyscrapers or how they blew up
Mhm.
two islands to build the Hong Kong International Airport or building the big dig in Boston kind of things. I got more interested in like the structural and geotechnical aspects of stuff, and I thought I was going to be more of a structural engineer. So I was still centering on stuff around the civil engineering field. And then in undergrad, I took a trip to India to visit some of my friends there. And it was the first country I went to where the culture was just like amazing and all of this kind of stuff. But it was like one of the first places I visited where I saw a lot of pollution related stuff. So the friend who
Okay.
was going there and visiting, as soon as we landed in the airport, he was like coughing in the Calcutta airport. And he said, this is just something that happens to me every single
Oh,
time
wow,
I
yeah.
come home. So there was a lot of air pollution. There are lots of issues related to solid waste management. It was the first country I went to where you couldn't drink the tap water or anything like that. We were talking about stuff related to like the Ganges River and the historical significance of it and the religious significance of it to Hindus. And I was asking my friends, okay, you guys are Hindus. Do you ever like washing the river as a part of like
Mhm.
religious significance of this? And they're like, we would like to, but we just don't because it's really, really polluted. And I thought, wow, this is really interesting that they're telling me about the religious and historical significance of this, but they're also really mindful about the pollution. So that got me more shifted towards the part of civil engineering that's focused on the environmental aspects. And that's where, I decided to focus.
Wow, okay. That's quite interesting, especially, again, you have this real personal experience that really kind of brought you into it.
Yeah.
So, since this being kind of a podcast style, I would like to
hmm
kind of lay down some general information about it for those that may not be informed. So I'm just going to read out some stuff if you don't mind. So protecting our drinking water really began with the 1974 Safe Drinking Water Act, but we got more focused in on lead and more stringent controls for that with an amendment in 1986. And this restricted the use of lead in new plumbing materials. Yet previously installed lead pipes were still being utilized. Then in 1991, there was the lead and copper rule, and that was published by the EPA. This regulation implemented stricter controls with how lead and copper can be in drinking water. Does that sound about right? That kind of covers
it does. Yeah, that's a really good summary.
So then my question for you, Sheldon, is while these regulations lay the groundwork for protecting drinking water, lead and copper contamination remain a concern in distribution systems today, with lead often being the primary focus. From your perspective, how effective has the lead and copper rule been in addressing these risks?
Sure. So I think there are studies that have demonstrated that since the implementation of the rule, we've seen a significant decrease in the amount of lead contamination in drinking water, including a decrease in consumer exposure to lead. So we've seen decreases in blood lead levels. Some of that is attributable to also decreases in air pollution from lead as well. So there has been improvements over the last several decades, but the goal of the rule is not really to get to zero, right? So when we're looking at developing a regulation, what the EPA does is they do some kind of risk assessment and they figure out what's the safe level that we could potentially have if it exists. And then we try and set the standard as close to that safe level as possible. In the case of lead, the maximum contaminant level goal, so the goal that we're trying to achieve, what people may consider to be safe, is zero, right? So, however, it's really, really hard to get to zero. Based on the treatment technology that we have, we can reduce the amount of lead that we have in water, but it's not really possible to get to zero. So even though, the tap water that you guys might drink in Denver or Boulder might be really, really good tap water, and we might consider that water to be safe, that doesn't mean that there's zero contamination and there's zero risk that's in that water. There are carcinogens that are in the water, for example. And when we said something is safe, it probably just means that there is a really, really low risk of something really bad happening. So the way the regulation is structured is it's based on a 90th percentile, right? And this makes people somewhat uncomfortable. So if you imagine that you go to 100 homes in Denver and you collect one sample from each one of these homes, 90% of those samples have to be below 15 parts per billion. It means that the other 10% can be any concentration. And the goal is zero. So that's the compromise that the EPA has made, where we can't really get to zero, but we're going to do the best that we can with the technology that we have and the feasibility that we have in order to meet this regulation, because we can't set a regulation that people can't meet, right? So we at least need to set a regulation to some degree where it reduces the risk, but not so stringent that utilities can't meet this regulation.
Sheldon, that 90th percentile is interesting to learn about. And do you think is a good way of determining whether or not the drinking water is safe as a whole?
Yeah, so that's a really good question. So the 90th percentile is specifically for, say, lead and copper in drinking water. If we're looking at, say, some of the carcinogens that we have, we're using different metrics. The reason why the EPA ended up landing on, say, a 90th percentile was also because of a negotiated process and also because of the characteristics of lead contamination in drinking water. So, for example, lead release can be really variable, right? If you have a high amount of variability, then it might be very difficult for you to use, say, an average, because the concern is I go to 100 homes in, say, Denver or Boulder, and in almost every single home, I measure zero in every single home. And there's one sample that's really, really, really high, and that makes my average really high. So now I'm saying my entire city is out of compliance based on a single high sample in a single home. So the compromise there is, rather than using an average, we'll use a 90th percentile, where we know that 90% of the samples are below this level. But there could be 10% of that population that could have elevated lead levels in their homes. So it was just because of the variable nature of lead release why they ended up choosing that 90th percentile.
Okay. So I feel like a lot of reason why a lot of this is talked about so much today, I mean, of course, there are those who have always cared, but what happened with like Flint, Michigan is I feel like what really led us into this whole awareness about lead pipes and getting these things changed out. So even though this was, Flint was a pretty extreme situation and there's a lot of other things I know that went into that, I feel like that was a big reason why people are talked about it. So would you mind giving us a quick overview on why lead exposure is such a concern for people's health? Are there any groups that are affected more or less than others?
Yeah, so you're right that lead has been a concern for decades. And if we think back, going back to the Roman times, for example, they still recognize lead as being potentially problematic, for example. But Flint, Michigan was really a catalyst for a lot of public awareness about lead contamination in drinking water. And there were other previous events like lead contamination events in Washington, D.C. in 2004, for example. In terms of why people should really be concerned about this is it can really affect every single major organ system in the body. Particularly groups that are of concern are children, especially young children in their early developmental stages, because it can cause decreased IQ in a permanent way. Other folks who could be at risk are pregnant mothers, for example. So in the early 1900s, for example, doctors used to prescribe lead pills to induce abortions. And in some cases, those lead concentrations aren't very different than doses that you could have in drinking water. So because of that, they're particularly of concern to, say, pregnant mothers or pregnant women as well. So those are probably, it'll affect, the general population, but those are two groups that are particularly susceptible.
I didn't know about the lead pills. That's actually pretty crazy. We've seen in recent years that the EPA they're implementing replacement of lead service pipes. And I believe the goal I read was within 10 years. With utilities now investing heavily in that transition, do you think the current policy framework adequately supports those efforts being put in by these utility companies?
Yeah, so I definitely think it'll cause us to have an improved public health benefit over the current rule that's there. Obviously, there's going to be criticism of any particular regulation, and there's going to be no perfect regulation or rule that's out there, but it's at least moving in a direction where there's going to be significant reduction in terms of lead exposure, because the goal there is to strengthen corrosion control treatment. They've lowered the threshold for the regulatory standard, and they're also requiring that utilities remove the major source of lead, which is those lead pipes that are there. So the rule is really targeting some of those really critical components that are major sources of lead exposure in drinking water.
And I was curious as well. I tried to do some research, but nothing was too consistent on exactly what was supposed to be replacing the lead pipes. I've seen some copper, but I haven't seen anything too solid on exactly what it was.
Yeah, so the major material that's going to be used for like replacing lead service lines or galvanized iron pipes will be copper pipes. So copper pipes tend to be less toxic, they're less resistant, and they're extremely durable. Plastic pipes, for example, could be one potential replacement, but in some of those cases, you could have leaching of organic contaminants from soils from the outside through the plastic pipes, which is something that doesn't occur with copper pipes. So for the most part, utilities are going to be replacing these lead pipes with copper pipes.
Okay, and to transition a little bit, so there are several corrosion control treatments. Of course, we know about the pH and alkalinity. There's the orthophosphate, blended phosphates, sodium silicate, just to kind of name some of the major ones.
Yep.
Even with all these established regulations and treatment strategies in place, what makes corrosion control such a persistent and complex challenge?
Yeah, so that's a really good question. So one of the reasons why it's challenging is that there's no one size fits all, right? So depending on your water quality, you'll have to tailor that corrosion control treatment to meet that water quality. So it could be cases where pH adjustment works really well in this particular water, or it could be I can't use pH adjustment at all because I have a really hard groundwater. And if I raise my pH, I'm going to start precipitating calcium in my system. I'm going to start closing up my pipes and not be able to provide fire flow anymore because I have so much scaling that's going on. So that could limit what you could potentially do. You also have to have simultaneous compliance. So you can't meet one regulation and then violate some other regulation. For example, if you raise your pH to control for corrosion, in some cases that tends to produce more of a certain type of carcinogen, so trihalomethanes. So maybe you raise your pH and now you have a violation of trihalomethanes. So you have to be thinking about not just the target, but the potential unintended consequences as well. So you're trying to meet simultaneous compliance requirements, and you're also trying to tailor this for my specific water quality, whether that's a certain type of surface water or a certain type of groundwater quality. So it's not going to be a one size fits all. So you have to test each water quality to make sure it will work in your system. And then there could be systems where they have lead pipes, copper pipes, brass, iron, and you're then trying to figure out, okay, how do I make sure I control for the most toxic contaminant, making sure I don't cause a different corrosion issue? Or there could be systems where the only metal I really have in my system is copper and brass, and I'm only focused on optimizing for that one metal. So you also have to account for the materials inventory that you have.
Yeah, I was actually quite curious about that too when I was reading over everything, because I mean, there's no way one system has just strictly one type of pipe, one type of, I would imagine that there's multiple of these systems that have to be put in place at a time.
Yeah, so what you'll typically do is you'll usually target your corrosion control to make sure that you are controlling the most toxic metal or the one of the greatest concern. And in some cases, you're doing that at the compromise of some other one that's there. So you're trying to achieve this balancing act, for example.
Okay. Wow, so it's kind of have to pick and choose where you want to win and where you want to lose.
Yeah, exactly.
Sheldon, so do your lab models, do those translate to what you see out in the actual field well?
Yeah, so that's a really, really good question. So there are different degrees of studies that you could do, right? So you could do what we call desktop studies, where you're looking at these theoretical solubility models to see, is this going to predict that I have a low dissolved concentration of these metals? I'm tinkering around with my computer or doing some math by hand. Another approach could be bench scale study, where I might just get little coupons and I might put them in a jar with different types of water quality, and I see how much metals leach off of each one of these. The next thing I could do is I could dig up a pipe from a system and bring it back to my lab and install it, or bring it to the utility and install it there. And I run the water in a very controlled way through those pipes. So that's more of a pilot scale experiment. Or I could do an experiment at full scale to see how well a treatment is going to work. So those will give me different degrees of certainty. If it's a desktop study and the theory, that's the least amount of certainty I have, but I can run the most amount of conditions because I'm just doing it on my computer. If I'm doing the bench scale study, it might give me some good sense of the direction in which things may go. Is it going to increase or decrease? But it's going to over-predict the concentration that you would expect to see in a system, but at least know the direction in which things are probably going to go. And I can test fewer conditions than the desktop there. And then the pipe loop studies, where I'm actually digging up something from a system and then installing it, I could probably only test maybe 3 conditions. They're extremely expensive to run. They're really, really complicated, but I have a greater degree of certainty. And then the highest degree of certainty you're going to have is at full scale. But that's going to be your greatest risk, because if it doesn't work, that's also what your customers are seeing. So usually you'll use multiples of these, where you'll start off with your desktop study that helps you to narrow down some conditions. You know what conditions you might test at the bench scale. Maybe you use that to help you narrow down some more conditions. And I know the 3 conditions I want to test at the pilot scale. And hopefully the pilot scale works really well in predicting what's going to happen at full scale. And at full scale, I hopefully have a greater degree of certainty that if I make a treatment change, it's not something that's deleterious to my customers.
Mm-hmm. So I feel like once you do implement something like that, you got to be pretty certain. I imagine there's a lot of backing of research that would have to go into that before you can implement
a
full-scale system.
Exactly. So there's going to be a great degree of research that goes into it. And then this is not something that the utility is doing independently. So the utility will typically do that, either their own internal research or hire an external consultant. And they also have to do this in coordination with the regulator. And they have to have approval from the regulator before doing this. So the regulator is going to approve the plan that they develop. And it's going to be based on the studies that they've done previously or things along those lines. So hopefully, along the way, there are multiple checks to make sure that, nothing bad happens. There's still cases, like you brought up Flint, Michigan, where there's still circumstances where bad things happen, but the rules and the structures are hopefully designed to mitigate against those things.
Got it. So this is kind of a good little segue into your research thing, because I know by what I've seen, please correct me if I am wrong on this, you are looking at pH as an alternative for corrosion control. Correct. With that, so what question are you trying to answer when you begin to look at pH as part of the corrosion?
Yes. So usually when a system is making a corrosion control treatment change, the typical methods that they're testing is the addition of orthophosphate, which is a corrosion inhibitor, or pH adjustment. So those are the 2 main ones that utilities tend to use. If you have lead pipes in your system, orthophosphate addition works really, really well for controlling lead release from lead pipes. It works fine for copper corrosion control, right? And these, obviously, there are exceptions to this. This is just like broadly speaking. So it works really well for controlling lead release from lead pipes, but maybe it works fine for copper corrosion control. But there's some downsides to using orthophosphate. It could cause increased microbial growth in your distribution system. That there are also downstream impacts where that water ends up going to your wastewater treatment plant. And now the wastewater treatment plant has to remove phosphorus. And if that phosphorus isn't removed, then it would end up in streams. When that water ends up in streams, then that could cause algae growth and eutrophication as well. So there are some potential downsides by using this. The regulations don't consider the downsides at all. They just say you need to choose the best treatment for lead, right? Even if it's going to cause an algae bloom somewhere downstream, right? That's you don't have to consider that at all, right? So now the wastewater treatment plant that previously wasn't designed for phosphorus removal may now have to upgrade their treatment plant to have phosphorus removal or things like that. Otherwise, they could have eutrophication and things along those lines. One thing that you brought up before, Kory, was that the EPA is now requiring that all of these systems replace their lead pipes. Now, if you replace their lead pipes, then the key motivator for installing orthophosphate is now gone, right? So do we still need to be dosing orthophosphate when there are all of these negative potential impacts? So if that's the case, and there are systems now that are currently using orthophosphate, but they don't have lead pipes anymore, can we transition from stop dosing orthophosphate to then shifting to a pH adjustment corrosion control? And if that's the case, then how do we do that in a way where it's really boring, right? Where the customers don't notice that there's a change. We're actually improving the corrosion control for the metals that are still left in the ground, like the copper or the iron that might still be left there. How do we shift more towards optimizing for those metals since the lead is no longer in the system? So that's the closer look that I'm trying to take for that part.
Which kind of leads me into, so I know you talked about it a little bit. So how are you running these tests? I know you talked about the coupons. Is that the primary approach to your current research?
Yeah, so we're doing this very large coupon study where we're trying to test a bunch of different conditions. So, for example, transitioning away from orthophosphate, right? So, like I described before, where you do a desktop study, coupon study, pipe loop study, and a full scale study, for example. We've kind of done an initial desktop study, and now we're doing a coupon study to see, are we going to have some kind of release that occurs if we stop dosing orthophosphate? So, for example, one condition that we're testing is a control, where you have different metals like iron, brass, copper, and then you just have orthophosphate at your regular pH, which is about 7.5, and that's our control. Then we have another one where our pH is 7.5, and you just stop dosing orthophosphate. Maybe that will be fine. At least the initial data says it's not going to be fine. You're going to have release of metals if you just stop dosing orthophosphate. We have other conditions where you keep the orthophosphate and then you raise your pH first, and then you allow the metal to adjust to that new pH condition, and then you stop dosing orthophosphate. We've found that doesn't really cause a negative effect, right? So at least the initial data is suggesting that there are approaches that you could use to shift away from this where it would not necessarily have a negative impact. So once we narrow down a set of conditions where we think it's going to work, then we'll test that at a pipe loop, and we'll test a few conditions. Because remember before I said we can test a lot of conditions in these jars, but because the pipe loop studies are really expensive, we really need to choose carefully which conditions we're going to be testing at the pipe loop stage. So that's the experimental approach that we're taking.
And when you run those pipe loop experiments, how long does it take to get your data back?
Yeah, that's a really good question. We had a guest speaker here yesterday from the Southern Nevada Water Authority, which is one of the most innovative utilities in the country, and they were talking about bend scale, about corrosion studies that they did, and they said it's like watching paint dry. If you do studies on, say, some of these carcinogens, you could get data back in a day, for example. If you do studies on corrosion, the coupon studies could take you like several months to get any data, and the difference is you can't stop the experiment. If you stop the experiment, then you're going to mess up the experiment. So you'd have to start all over again. So they're really laborious and slow experiments. If you're doing the pipe loop experiments, those could take years to run. So it could be 6 months to 2 years to run those experiments. And again, it's long, slow experiments that you're doing there. So that's a really, really good question.
Where you're currently at with the research, where are the biggest uncertainties right now?
So I think one uncertainty is that this has never really been tried before. And in systems where there isn't very good precedent for this. So the only precedent I can really think of was Flint, Michigan. And that wasn't a very good precedent, right? Where they were on a system that was using orthophosphate, and then they switched to a system that wasn't using orthophosphate, and it was a really terrible circumstance. So I think a great degree of uncertainty is, we can get data from our experiments, we can get data from our pipe loops and things like that, but how well does this really translate to the full-scale system? Because even for the traditional corrosion control studies that we do, usually we can find what we call an analogous system, where there is some other utility that's done this before and it's worked there. The drinking water community tends to be very conservative in terms of their approach, because when things go bad, the implications can be really, really big. You're talking about cities of tens of thousands, hundreds of thousands of people who could be impacted. So utilities will be apprehensive to try this, where it's just like, if it's not broken, I'm not going to change, because I don't want to be the first one to try this. And I don't want to be the first one to try this and then end up in the headlines because there's some unintended consequence that we just didn't anticipate. So I think the uncertainty is going to be, how does this really translate to what happens at a full-scale system when nobody has really tried this before at a full scale? And I think it will be an uphill climb to be able to convince any utility that doesn't have any issues right now that they should make this change.
So with that, then, I know you kind of answered a little bit, but so let's say you get these results, you see that it is an effective method. What would need to happen before utilities could consider changing strategies for this?
I think we would need a lot of education and a lot of buy-in from different stakeholders, right? So you would have to have buy-in from the public. You'd have to have buy-in from your regulator. You'd have to have buy-in from the utility. You'd also have to have buy-in from all of those downstream users as well. So not just the drinking water plant, but the wastewater plant and the people who are concerned about things on the clean water side of stuff. So those folks who are concerned about, are my rivers and streams and lakes, swimmable and fishable? You'd have to have buy-in from all these stakeholders involved, and really, really compelling data to suggest that there's going to be no negative public health impact and there's only going to be upside. So I see this as probably a really interesting scientific and academic experiment. I am a bit more skeptical about the extent to which there's going to be large-scale adoption in the near term related to this, only because, like I mentioned before, it's a very, very conservative community. And if something isn't broken, then they're really not going to be inclined to try and make some large wholesale change related to this. So, and this is where, as scientists and engineers, we might be focused on the stuff that we can do in the lab, communicating our data, getting that published in good papers or things like that. But there's also a communications aspect to this as well. There's a public policy aspect. There is, communicating with the public about this stuff and getting stakeholders on board, which is not always something that you get training on in a typical engineering or science classes. For example, is how do I conduct community projects and stakeholder engagement? There are communications experts that we typically work with on that stuff, but usually it's not one of those things where we have a lot of classes on calculus, lots of engineering classes, lots of math classes, and not as many on, public engagement.
Sheldon, would you say the catalyst for change comes from the bottom, as in people talking and creating a voice for themselves, or does it come from the top down, where it's more so the stakeholders that are going to be in charge of there being any changes moving forward?
I don't know. That's a really good question, and I don't know, because I think even some of the stakeholders, it would take a lot to get their buy-in. Right? Because the last thing that they want to do is something that's going to negatively impact their community. Right? So I think they would be really apprehensive about saying, why am I going to go with this innovation when everybody seems comfortable right now and everybody seems safe? Why am I going to make this change where it seems like it's good, but I'm not sure? So I think even just getting the stakeholders on board, and these stakeholders may understand the science, they may understand the data, they may believe the data, and they may be like, I don't want to be the first here. If I see that there's 24 other systems that have done this and it works really well, I might consider it, but I'm not going to be the first one.
Before we start closing things out, for anyone who may be interested in water quality, or environmental engineering, what would you consider to be the most impactful skills or traits entering this field?
I think some of the most impactful skills might be writing. In almost any job that I've seen, whether you're at a regulatory agency or you're a professor or a researcher or you're working in consulting, you have to write reports and be able to communicate that to the client. You have to be able to write proposals to actually win. You have to be able to write papers that are communicated well enough that they can get published. So a really big part of the job is communication and writing and having really solid writing and communication skills. I think thinking creatively is also a really important aspect of that. And I think if you are working as an experimentalist, then stick-to-itiveness. And because what ends up happening is many times experiments fail. right? And you have to get accustomed to failure a lot and be able to still be motivated, even when sometimes your experiments don't work. So I would say stick-to-itiveness, thinking creatively, and writing and communication skills are probably some of the biggest ones that come to my mind.
I agree. I mean, imagine having all this information, but not knowing a way to tell people. I feel like
exactly.
It's a need. Are there any misconceptions that people may have about the safety of drinking water?
Yeah, I think one of the biggest misconceptions I can see is that there's a zero risk tolerance among the public, for example. And when somebody says to me, is my water safe to drink? That's like a really uncomfortable question for me.
Yeah.
Right? Because when I hear safe, what I hear is your risk of something bad happening is 1 in 10,000 or 1 in a million. Right. That's the standard that the EPA is using, where if I'm exposed to some carcinogen, there is a 1 in a million chance of some excess case of cancer that you could get. But it doesn't mean that the risk is zero. Right. So what does safe really mean? And I think when the public hears the word safe, the way they interpret it is there are no contaminants in my water. When I hear the word safe, what I hear is that my risk is very low of getting sick. I think that's like a misconception that safe water means there's nothing in my water. That's like there's no contaminants, and there will always be, for the most part, something that could be there. Like the water isn't sterile, so there's bacteria in your water, even when it's disinfected. If you disinfect your water, it's forming carcinogens to protect against the bacteria that's in the water. And there could be other things that we're just not measuring, like PFAS or personal care products or pharmaceuticals that aren't removed during treatment. So I think for me, that's one misconception that I've typically seen.
Yeah, I feel like a lot of things can easily get blown out of proportion as well. And so for our final question here, so after working and researching in this field for years, what drives you to continue researching corrosion control and water quality?
I think it's fun. And I think I get to work with people every single day, especially the students who are much smarter than I am. Right. And I get to just see like light bulbs go off all the time, and I get to learn a lot from them. And my colleagues are really smart and really innovative and help to drive me along. And then the nice thing is also seeing the impact of your work. Right. So in some cases, I've been involved in projects where we implement something like a disinfection system that mitigates an outbreak, a disease outbreak that was going on. And it's nice to see the impact of that work. Now, will the public know who I am? Or will the public know that I was involved in that project? Probably not, right? I think if you're an environmental engineer, probably you might have a greater impact on public health than, say, a doctor. But the public is probably not going to know who you are. Right. And if you look at, there's a study that was done on the greatest public health innovations since 1840. Right. And they looked at things like pain medications and vaccines and antibiotics. And what these group of experts came up with was clean water and sanitation. It has done more to save lives across the world than any other public health invention that's there. But you probably know the names of your doctors that have healed you, but you may not know the name of the water treatment plant operator in your local town that's making sure that you have clean water every single day. So I think, I get some joy from that, knowing that there is impact to the work and that I get to work with people every day who are excited about what they're doing and much smarter than I am.
It sounds like then you're in a field where headlines aren't really sought after.
Nope.
Yeah.
Boring is good. Boring is good.
Yes. Yeah, exactly. if we make a treatment change that improves water quality and the customers didn't even know it occurred, that's a good day. But if you make a treatment change and it's exciting and it ends up in the headlines, that's probably not a good thing.
Yeah.
Yeah.
All right, so any closing remarks from you, Sheldon, before we put the final stamp on this?
Not really. Just wanted to tell you guys thank you for the conversation and for reaching out. It got me thinking about a lot of things that I wasn't thinking about before. And good luck with your project. And tell Randy hi from me the next time you see her.
We'll do. We'll do.
Thank you so much for
yeah.
All right.
Yeah. Thank you so much for taking the time. You take care too.
Yep. Bye.